Hello again, everyone, and welcome to lesson 2 of our unit on chemical reactions. Today's lesson is going to be about synthesis and decomposition reactions, as I mentioned at the end of the last lesson. And we're also going to talk about how to balance chemical reactions. So, let's start by talking about what a reaction is. So reactions, or chemical reactions, are anything that results in the formation of a new compound or a new chemical. So today's focus is going to be, as I mentioned, on synthesis and decomposition reactions. So we're going to introduce the topic using those. Now, the most generic type of synthesis reaction is two simple things that we can call A and B, both separate at first, coming together to form a compound AB. The opposite of this would be a decomposition reaction. In which one thing that we can call AB breaks down into its components A and B. So the first thing to mention about chemical reactions is that there's two sides of chemical reaction. There's the left side, which we call the reactants, because these are what we're putting together, or what we're using to make the stuff on the other side. So the left side of the reaction is called the reactants, the things that are reacting to form what we call the stuff on the left side, known as the products. So even though there's two things on this side and one thing on this side, and just one thing on this side but two things on this side, these are still the reactants of this reaction because they're on the left side of the arrow, and this would still be the reactants because it's on the left side of the arrow, whereas these would be the product, or this would be the product of this reaction, and these would be the product of this particular reaction. So let's get started with using a couple synthesis reactions to demonstrate how to write chemical reactions. So we'll start with synthesis. So among the simpler synthesis reactions is the synthesis of water that we saw last lesson as being H2O from its elements H2 and O2. H2 represents hydrogen and O2 represents oxygen. It's worth it to take a minute here to extend our ability to name chemicals by identifying why H and O both have that subscript 2. Now, there are certain elements on the periodic table that will never exist by themselves. Last lesson we looked at things like sodium and lithium that can exist as single atoms, Na or Li. Whenever whenever hydrogen or oxygen exist by themselves, they have to exist with a partner of themselves. So as we talked about last time, the subscript applies to the number of hydrogens in this compound. Hydrogen never exists as just an atom, but rather as a pair of atoms in a molecule known as the hydrogen molecule. The other elements that do this are oxygen, as you can see here, and we use a little acronym for the rest. The acronym is Hoff-Brinkel. A bit of an awkward acronym, but H is for hydrogen, meaning that if anyone ever tells you hydrogen, then you hear H2. If anyone ever tells you oxygen, then you hear O2. If anyone ever tells you fluorine, then you hear F2. Similarly with bromine is Br2, iodine is I2, nitrogen is N2, and lastly Cl, chlorine, is Cl2. That being said, this reaction is the reaction of hydrogen and oxygen to form water. If we look on either side of this chemical reaction, and we use our counting atoms from last lesson, we can see that the left side has a total of 2 times H atoms and 2 times oxygen atoms. The 2 representing the number of hydrogens here and the 2 representing the number of oxygens here, whereas the water has, the 2 represents the number of H's, 2 times H, and the water also has just only 1 oxygen, as there's no subscript. So the law of conservation of mass tells us that no atoms can be created or destroyed in a chemical reaction. That is to say that if we had 2 oxygen atoms at the left side of this, there better well be 2 oxygen atoms on the right side after the reaction is complete. So this means we need to do something called balancing chemical reactions. And that basically implies that we add coefficients or numbers before the chemicals to multiply the whole compound such that we can balance the number of atoms. So let's take a look at what that means. The first example here, or the first issue here, is that the number of oxygens is not equal. In order to make the number of oxygens on this side equal to the number of oxygens on this side, we need to basically double the number of oxygens, since we only have 1, to get to the 2 oxygens we had originally in the reactant side. So we add a coefficient before the whole molecule. It's important to never change the subscripts, but rather add a coefficient in front of the molecule that doubles the total amount of molecule you have. So after doubling all the H2O we have, we now have 2 times the 2 we had before of hydrogen, meaning we have a total of 4 hydrogens. And in terms of oxygen, we now have 2 times the 1 oxygen we had before, so we now have 2 oxygens. If we look at the right side now, there is a total of 4 hydrogens, which is no longer equal to the number of hydrogens on the left, so we have to go back to the reactants and say, we need to now double the number of this hydrogen molecule we have, and since the hydrogen molecule had 2 to begin with, we now have 2 times 2 hydrogens, and a total of 4 hydrogens on the left. So now the number of hydrogens on the left and right are equal, the number of oxygens on the left and right are equal, so on the right and left are equal, and we have a balanced chemical equation. So when we represent this chemical equation, or this synthesis with 2 elements coming together to form a compound, we have to represent it with 2 water molecules being formed, 2 hydrogen molecules being consumed, and only 1 oxygen molecule being consumed. These are the reactants, and this is the product in a synthesis reaction. As mentioned, decomposition reactions are the exact opposite of synthesis reactions. So decomposition reactions, or a good example of a decomposition reaction, would be the reverse of this reaction. And that would be water, H2O, breaking down into its elements, hydrogen and oxygen. In this decomposition reaction, it's balanced in the same way, such that 2 hydrogen molecules are produced and 2 water molecules are consumed, and only one oxygen molecule is produced. This is an example of a decomposition reaction because one compound, AB, is breaking down into two compounds, A plus B. So I should have labeled this as a decomposition reaction. Whereas this up here is an example of a synthesis reaction. Two things coming together to make one, and we also talked about how to balance chemical reactions. Let's take a look at one more synthesis reaction. The next synthesis reaction we're going to look at here is iron, solid iron. So since iron is not part of that Hofbrinkel acronym I showed you, it does not have to have a 2 when it's alone. But it's reacting with oxygen. So I would be telling you these names, for instance, on a quiz. And we can start from there if that's preferable. But iron reacts with oxygen to form, I'll move this down, we'll write this after, iron oxide. And it's important in this reaction that we state the charge of iron, so we're going to say that it's iron 3 oxide. And you don't need to worry about this too much, but just keep in mind that if you see a Roman numeral inside a bracket like this, it's telling you the charge of the metal before it. So this would be iron 3 plus, because the 3 represents the charge of the iron, and oxide, as we saw before, had a charge of -2. So why is that important? Well, when we convert this, so let's do this as a bit of an example. But when we convert this compound into its actual, or this reaction I should say, into its actual chemical compounds, iron by itself is just represented by its element, Fe. Oxygen, because it's one of the things in that Hofbrinkel acronym, has to have a partner always, and it's always O2. These are reacting to form the chemical iron oxide. Before I can just write what iron oxide is, I need to consider what the chemical formula of iron oxide is. And to do that, we have to use our crisscross rule from before. So Fe, we said, is 3 plus, because the bracket tells us that. And oxygen is -2, because that's its charge from the periodic table. Now we crisscross them down. And we find that iron 3 oxide is actually Fe subscript 2 from the charge of oxygen, O subscript 3 from the charge of iron. Now looking at this chemical synthesis, again the atoms are not balanced. On the left side we only have 1 iron and 2 oxygens, whereas on the right side we have 2 irons and 3 oxygens. So this is where we're starting from. We're saying we need to get the number of ions to be equal. As a general hint, I like to save oxygen and hydrogen atoms last. In the last example we only had oxygen and hydrogen, but in examples that have more than just oxygen and hydrogen, I like to balance my oxygens and my hydrogens last. So I'm going to start with balancing the number of ions. If we look at the right side, how many irons do we have? Well, it's Fe2O3, so we only have 2 iron atoms on the right side. On the left side, because iron is by itself, we actually only have 1 iron atom here. So in order to balance the 2, we can simply put a subscript of 2 before the iron, making it so that the total number of irons on the left is 2. Next, we have to balance the oxygens. This is kind of a tricky one when you see that you have a 2 on one side and a 3 on the other. But as a general rule of thumb, it's pretty safe to put a 3 on whatever has the subscript 2 and a 2 on whatever has the subscript 3. When we do this, we also unbalance the number of ions. As a result, we now have 2 times 2 ions here and 2 times 3 oxygens. The 2 times 3 oxygens is good because we now have 6 times oxygen, which we have 6 times oxygen here now. But the ions, the 4 times ions that we now have, 2 times 2 to give you the 4, is not balanced with the only 2 ions that we would have here. As such, we have to double this again, making it into a 4, so that 4 iron atoms are being consumed with 3 oxygen molecules with a total of 6 oxygens in them to form 2 Fe2O3 molecules in a synthesis reaction. Again, it's a synthesis because 2 things are coming together to form 1, whereas decompositions are 1 compound breaking down to form 2. Sorry about the screen shake. And now our reaction is balanced. So the next 2 lessons we're going to be doing are going to be single displacement and double displacement reactions. And from then on, we're also going to talk about combustion reactions, and that will sum up our unit on chemical reactions. Thanks again for tuning in, and we'll see you guys next time.